a vector? I can almost see everything. I'll tell you what, that black on red, just somebody needs to figure out fonts, I'm telling you. Alright, so if y'all look up here real quick, so this is a vector. It is, what would y'all call a vector? If you saw that, what would you call it? Like,
Array.
What's that? It's array? But it is not array.
It's a line.
It's not a line. It's less than array, but it's more than a line. Okay, technically it's less than a line because geometrically, remember, a line extends in both directions infinitely. Right? Or were you able to get this? Okay. Trey, you got it?
No line.
He's there. Okay, so we're closer. So it's not array, though it does kind of look like array. Array starts at one point and goes forever and ever and ever. Okay?
Line segment.
This is a line segment. Now you're like, wait a second, line segments, I know line segments, they have a dot, and there's something there, right? Well, okay, so we're being kind of tricky here. There actually is a dot here and there is a dot there. So it's a line segment. But it's a line segment plus. Okay? What's the plus? What's the additional feature here, ladies? The direction. The arrowhead right there. Yep. So, well, you might think, oh, this goes on and on forever and ever. Nope, it does not. Vectors have a beginning point and an end point. And the end point is right here. But that little arrowhead is just telling you that this vector is traveling, is pointing in that direction. As opposed to, say, maybe this vector. Which has the same length, approximately, and let's get it right, just right, but anyway, same length, but different direction, okay? So, there you go, that's what the arrowhead is for. Yeah, feel free to put all sorts of vectors. As you can see, a vector is not tied to any one particular location, though I am going to tell you a lot of the vectors that I'm going to be drawing, we're going to start them at the origin, but they don't have to start at the origin. I do actually really like this simulation more than others that I've seen because there's no XY grid, right? I mean, there's no like, where's the origin? Because they've started. Vectors do not need to start at the origin. This, vectors can just float around. You can kind of put them wherever you want, okay? And like you said, there you go. Have some fun with that. And there's other stuff here that we will, like the components and the resultant. We're going to get to that. By the way, this is sort of a new unit in the middle of our trig, and this is subunit, I guess you call it, vectors. For at least 2 weeks on vectors. In your physics class, have y'all dealt with vectors? So you like are you already vector experts? Experts?
Oh.
Okay. So maybe you're not quite, but either do you have some questions about vectors? Are you kind of iffy on vectors? Or are you like totally weak on vectors? Is you either totally weak or totally expert, or you're somewhere in the middle?
We spent like 2 days.
2 days on vectors. Okay. We're going to spend probably more than that. So, but you're done with vectors. Yeah, well, the thing is, you might think so, but in physics, you're never really done with vectors because the more you learn in physics, then you find out that, and here's a new thing, and there's vectors with that new thing. And here's another new thing, and there's vectors with that new thing. Vectors are sort of like the numbers of physics. I mean, sort of like, they're everywhere, okay? And the more physics you take, the more vectors there are. There's even 3-dimensional vectors. We are only going to be dealing with 2-dimensional vectors here. Though I will say, and this is for Preston and anybody else, if you're dealing with a 3D world, like we actually live in, but I'm thinking also maybe particularly in a simulation setting, like Unity, or maybe an art setting, like Blender, or Maya, or any of those other artistic tools and stuff like that. Everything that I'll be telling you about 2D vectors just extends one more in the z direction to 3-dimensional vectors. So I'm excited here. All right, you got 1 more minute of play time. I'll let you play. Would you mind coming up here for attendance?
Okay. Oh.
I'm gonna just freeze it. Actually, this is Dominic. This is Dalton.
That's my bank account right there. That's my ROM.
All right. Go ahead and close those MacBooks and let's go ahead and get out the CD page.
Once you get on the link. It's so hot. Happy to get up.
There we go. Now you're free. All right, here we go. All right, class. We got a lot of writing, a lot of stuff we're gonna be doing here. So let's get going. So, what is a vector? A vector is a directed line segment. And a vector has 2 pieces of information. Anybody want to guess what those 2 pieces of information are? Direction is one of them. Say again? Magnitude. We'll say and has magnitude and direction. So 2 pieces of information. That's what a vector is. Now, that's in contrast to a scalar, which just has 1 piece of information, just 1 number associated with it. So the way you might talk about a vector is you might say, we have a vector that is 5 miles long in a direction 20 degrees north of east. And this is the way that you write vectors, write them down, is it's an ordered pair. That is to say it's a pair and it has an order, okay? But the number, and there's a parentheses around it, the number here is not the x coordinate, and the number here is not the y coordinate because it's not an ordered pair dot. It's an ordered pair, but this piece of information right here is the magnitude, and this piece of information right here is the direction. It's always going to be in that order, magnitude and direction. In case you're wondering what the heck is a scalar, okay, 5 miles. That's a scalar. 3 gallons. 2 miles per hour. Those are all scalars, just numbers. Yeah, there's a number in a unit. Yeah, it's a number in a unit, but that's a scalar, just a single number. A vector has a magnitude and a direction. So 5 miles at this direction. 2 miles per hour north on I-35. Yeah. Causing a traffic jam. All right? You might say, why vectors? Why you gotta learn about vectors? Well, you already kind of answered that question. Life is vectors. Okay? Physics is the simulation of the real world put into mathematical, conceptual terms. Okay? And the real world has vectors. So we've got to talk about vectors. What are some things? that are vectors. Displacement, if something's been moved, how far has it been moved and in what direction? This way, or this way, or this way, or down. Velocity is a vector quantity. Acceleration is a vector quantity. Force. Oh, it was pushed or it was pulled. Okay, but in what direction? And I don't just mean left or right, up or down. I mean, can you give me an angle? But yeah, there's also this going on. This was also pulling it down, and this was pushing it. Both of them at the same time. Give you the angles on that. We'll figure out exactly what path it traveled. If you haven't talked about it yet, you might. Momentum is a vector quantity. Normally, you don't really start dealing with momentum as a vector until like college physics, but you might. Some examples of scalars would be something like just distance, speed. So technically, velocity and speed, you might be like, those are the same thing. Well, technically, velocity is a vector quantity, and speed is a scalar. Speed is just the magnitude of the velocity. It doesn't tell you the direction. Energy is a scalar. Power is a scalar. There's lots of things that are scalars. Mass is a scalar. Volume, let's go with the 3 gallons right there, so volume is a scalar. Alright, so that's just to kind of give you an idea the difference between the two. Let me give you some diagrams. We're not really going to be dealing with scalars a whole lot. I'm not going to have like questions that are like, is energy a scalar or a vector? This is just background information. Not all of it is, but that one was. I'm going to draw a vector here for you, and unlike those over there, I'm going to start mine at the origin just because. So normally with vectors, I mean, when you talk about the vector as a single symbol, you put it's a lowercase letter, and sometimes if you want to be real nice and proper, you can put the arrow over top of it facing to the right. A lot of times myself and other mathematicians and all of us get kind of lazy, and we just write the arrow like one sort of arrowhead, like one half of it right there. There's like, so there's some notation for you. The magnitude is how long the line is. I'll abbreviate that with magnitude. The direction is the direction. The direction that the arrow is pointing. Okay? There are lots of different ways that you can talk about the direction. I could say 5 miles. Earlier I said 20 degrees north of east. But I could also just write 5 miles at 20 degrees. And calculus students everywhere would know, oh, 20 degrees, that means going at counterclockwise rotation starting at the positive x-axis, because that's standard notation. This is 0, this is 5, this is 10, this is 20. Okay, watch 20, something like that. It could be in radians. It could be 5 miles. This isn't exactly right, but I'll say pi over 10 radians. It doesn't really matter. I mean, those are all they're all still vectors. They're all a magnitude and they're all a direction. That's 20 degrees is not 5 degrees. Pi over like 6. What's 360 divided by 20? Pi over 18. Okay. That is just sort of your choice and whoever's giving you the problem, whether or not your angle here is using cardinal directions or standard notation, degrees, radians, positive, negative. You know, I can put negative 340, you know, all kinds of different stuff. In this situation right here, if I were to draw absolute value bars around the lowercase v, those really don't mean absolute value, okay? Just gonna let you know here, that's what it does with scalars, but those really are magnitude bars. And they're asking, what is the magnitude, the size, the length, whatever, of vector v? And I've told you here that it's 5, and that's 20 degrees. So the magnitude of vector v would just be the 5 miles. For those of you that are kind of interested, you might say, well, why would I always call them absolute value bars? Well, because when you're dealing with numbers, if I had, you know, x there, x is 7, right? The magnitude of 7 is, how far are you away from 0? And the answer is, I'm 7 units. If you're talking about negative 7, the magnitude of negative 7 is asking, how far away are you from 0? And the answer is still 7. So that's kind of a little bonus side lesson here. But those bars are really magnitude bars, they're not really absolute value bars. And I say that because we're applying them here, and you see them in other situations too. So better just to call them magnitude bars. All right. Obviously, if we had a longer line segment, then that would correspond to what? If I had something that looked like this. This is vector y. How does that relate to vector v? In terms of magnitude or direction? Taylor, what do you think? How does y compare to v? It's not a complex answer.
It's the same thing, it's just a different variable.
It is a different variable, but okay, let's talk about, I'll ask you 2 questions. Is the magnitude the same or different? Between y and v, magnitude. Or not sure? Not sure. Different. How are they different? It's the length, right? It's the same direction, but it's a longer length. So we're going to use terminology. Same direction, longer magnitude. So a number for this, if that was 5, this might be like 8. Okay? So y, vector y, has same direction as vector v, but a different magnitude. So if we were sort of guessing, we might say vector y might be something like 8 miles at 20 degrees, because it's longer. What about vector z here, class? Same magnitude or same direction? Yeah, different magnitude, same direction. Y'all see what we're coming through here? So magnitude is length. Okay? So if you need to write that down. Magnitude is the length. What might be a reasonable number for the magnitude of z? 2, sure. Z is 2 miles at 20 degrees. Now, does that make sense? The longer it is. Okay, what about this one? Wrap around the alphabet. There's vector A.
Magnitude is the same, directions change.
Yes.
Vector.
Oh, vector V, right. Y'all get that? Comparing A with V, A is approximately, that's what I'm trying to do here, approximately the same length, okay? But it has a different direction. So A has same length, which would be magnitude, but different direction. In fact, I try to make it so it has the complete opposite direction. So opposite direction is 180 degrees. So vector A would be something like 5 at, well, what's 20 plus 180? Oh, that's 200 degrees. So 5 at 200 degrees. You can take a vector and move it wherever you want. Vector A is not tied to this location, just like vector B is not tied to that location. I can grab a vector and move it anywhere I want. So if I wanted to, and I do, I'm going to move vector A right about here. And you can see that if we were to plot that, that would be about 200 degrees. You don't need to draw that necessarily, just be trying to show some different things here. Okay, we're feeling pretty good. Magnitude is how long it is. Direction is the direction. I'll draw one more. Maybe I'll make vector B. Preston, what's different about vector B?
Direction.
The direction is different. Okay, so I think we're getting the idea. Direction is the direction, and the magnitude is how long it is. All right. So I want to introduce some notation here. So I'm going to write this down. Just you already have it, so you don't need to. Vector B is 5 miles at 20 degrees. I want to talk about vector C, I guess. This part you can write down. Vector C is 7 times vector V. When you have a number like this, a scalar, multiplied by a vector, what you do is you just multiply the magnitude. Okay? So we'll write a note here. A scalar times a vector is a new vector in the same direction but with multiplied magnitude. So vector C is still going to be 20 degrees, just like vector V was, but the magnitude is going to be 7 times the 5 miles. So 35 miles. So if that's vector V, that would be like vector C. And I think that matches what we just saw a few minutes ago, where the length of the vector corresponds to its, oh, you are so awake, magnitude. Yeah, okay. The length is the magnitude. Okay. Let's keep going down the alphabet. If vector D is equal to 1/2 of vector V, then that would equal same direction, so still 20 degrees, but the magnitude is going to be 1/2 times that 5 miles. So that's 2.5 miles. So vector D would be like, oh, that one. What? I just used blue. Let's try this one. There you go, really small, vector D, half of vector V. So that's what happens when you have a scalar and you multiply it by a vector. Same direction, different magnitude. If you have a negative vector, so like negative vector V, now you might be like, oh, that just means the opposite, like negative times the magnitude. Actually, it doesn't. When you have a negative in front of that, it means something different, okay? Negative vector actually means the same magnitude, but opposite direction. Negative in front of a vector means same magnitude, opposite direction. So that would be 5 miles, and this is actually the one that we did earlier before. So it means add, you could actually add, or you could subtract 180 degrees, or add or subtract pi. It doesn't really matter. We know this from our experience. If you add 180 degrees, or if you subtract 180 degrees, you're going to end up at the same place. If you add pi radians or subtract pi radians, you're still going to end up at the same place. So in this case, adding 180 degrees to 20 degrees gives you 200 degrees, and that would look like this. Negative V would be pointing in that opposite direction. It doesn't look entirely opposite, so we'll try to. Would you all like to do an example of that? Okay, let's do an example of that. Vector M is 3 meters at 15 degrees. Nayeli, what would negative M correspond to? Keeping in mind that negative means the same magnitude, but opposite direction. 3M. And 195. Would you like to do another example? Or would you get it? Same magnitude, add 180 or subtract 180. I think we're good. I think we're good on scalar multiplication and negative vectors. What I would like to do is talk about something that's interesting. So it's sort of like vectors are kind of like a brand new like number system, all right? And when you first learn numbers, what's the first thing that y'all did with numbers? You counted them. Then what'd you do? Added them. So we just kind of we now know this new thing, these new numbers, okay, these new vectors, okay? And so now we're going to learn how to add them. What happens when you add two vectors? So new subsection. It's still vectors 1. Sorry, new subsection. So adding two vectors. So if I want to add vector A and vector B. It's a 3-step process. Okay, so I'll write the steps over here. So here's vector A. I'll make it like, I don't know. There's vector A and there's vector B. To add vector A and vector B. Step 1. Draw A. Now I'm going to actually apply those steps over here. So, drawing A. Step 2. Draw B so that it starts at the end of A. Draw B so that it starts at the end of vector A. Come over here, and I'll go to the end of vector A. That's where the arrowhead is. Step 3. Connect the beginning of A to the end of B. And you're done. So I'm going to connect the beginning of A to the end of B. And that is my vector A plus B. Another name for a vector sum is the resultant. There's the resultant. So A plus vector A plus B, that sum, aka also known as the resultant. Resultant. Okay? I'm going to draw some vectors over here, and this is just going to be some practice for y'all so you can understand that process. I'm going to draw 2 vectors, and then I want you to sort of, on your paper, combine them. Okay, so we can kind of get into practice of adding vectors. So, let's see. Vector A is going to be kind of up and to the left, and vector B is going to be kind of like that one. It's going to be just a little bit to the right. Then we've got vector M, which is going to be straight down, and vector N, which is going to be straight to the left. We should add those 2. Figure out what A plus B is. Figure out what M plus N is. Should take you about 30 seconds on each one of these tops. C is going to be a little kind of that to the right, or to the left rather. D is going to be kind of like that to the right. There we go. Left, right, whatever. C plus D. Let's go W up a little bit. X down a lot. Figure out what W plus X is. That should be enough. You get all those. So on your paper, go ahead and I'll give you about 2 minutes while I walk around. Try to do A plus B, M plus N, C plus D, and W plus X. Remember, you're going to first draw the first vector, then on the end of that you're going to draw the other vector, then you're going to connect the beginning of the first vector to the end of the second vector and call it good. Okay, that's fine. But then, which way is your arrow going to go? Your arrow's going to go from here to that. Now, which way is the arrow going to go down, Rory? Nope, other way around. From the beginning of A to the end of B. And which way is the arrow? Where's the arrow? On A plus B? Nope, it's on that, yep, from the beginning of A to the end of B. And just make sure, yeah, walk around. Look here, the arrowhead was at the end of B over here. So this is our beginning, and this was the end. So when we do A plus B, where our resultant is starting here and ending over here. All right, we give you 1 more minute. You guys have arrowheads? Good. All right, that's another minute here, class. So, let's go ahead and draw this. So, first off, eyes up here, we're going to draw vector A. So, kind of up and to the left. Then B was a little bit to the right. Now, it depends on how your scale was or whatever. I tried to make this one kind of small. You can do it a little bit larger than it, probably go a little bit farther to the right. And then we'll connect the beginning of A to the end of B. So right there, that's A plus B. So you should have definitely something that's up, and then depending on how far you actually made your B, maybe all the way to the right or whatever, but I'll go ahead and see if I can use this tool here for this next one. So first off, I'm going to draw a vector M, so that was kind of straight down. Oh, I got drag on here. Then vector N, which was straight to the left. Okay? And then I'm going to connect the beginning of M to the end of N. So if I show the resultant, it should be something kind of, well, doesn't seem very, very right now, does it? It would look something, kind of. Perfect. Not it, huh? I don't know what's going on with their calculations. Let's look at C and D here. C was up and to the left a little bit. Then at the end of that, we have D, which is kind of up and to the right a little bit, although I tried to make them about the same size. Whatever. And then, so it's kind of like zigzag. But the end result is from the beginning of C to the end of D. Maybe yours is straight up and down, I don't know. There's C plus D. We'll do this one over here. First draw W, which is up a little bit. Then at the end of that point, draw what I call it, X, straight down a whole lot. Okay? And so then, connect the beginning of W, which is right here, to the end of X, which is right here. And so, this right here is W plus X. If I grab it and pull it over here, it would look like this. It would just be straight down. Which, if you think about it, if you've got something pulling up, kind of weakly, you know, not a whole lot, but then someone else pulling down really hard, okay, which way is that object going to go? It's going to go down. So you can start to see how vectors kind of, sort of simulate forces, okay? If you have a force going this way and a force pulling the other way, if you add those two forces together, it's going to tell you what's called not just the resultant, but sometimes with forces, it's called the net force on an object. And we have just enough time for a quick demonstration. All right, Robert, you are the man for the job. I'm going to show you how vectors are really helpful. We're going to simulate this sort of thing right here. Come on up here, real quick. We got a minute. The neat thing about vectors, ladies, hold on. We're still out of class here. Okay. Robert is going to push the chair straight that way. Observe. With a force. Thank you. Okay, step back. Then I'm going to push this chair straight that way. Okay? Those are our forces in isolation. Okay? In fact, what we could do is we could do his first, then mine. Go ahead. His first. Then we can do my force exactly that way. It ends up right here. But what's interesting is that if both of us push this at the same exact time, the end location is going to be the same as if we were to separate those two forces. Observe. I only want you to push that way. All right? And I'm only going to push that way. Ready? 1, 2, 3. You pulled that way. I didn't know I did that. I pushed it forward. Show us palm straight there so we can see. All right? And I'm going to just push out. Ready? Set, go. Y'all see? Are y'all a believer?
No.
The resultant location, the resultant force, was the same as if I had just done this. Push it diagonal. Okay? Tomorrow what we're going to do is we're going to add up, yes, thank you, Robert. We're going to add up some vectors by hand and kind of see what happens when we do that. And then also we'll see why adding them up by hand is a really annoying process. That's vectors. Thanks for watching. See you tomorrow.